Hi, in this video we'll showcase how the core-independent peripherals of the AT-Tiny817 can be used to make an accurate and deterministic ultrasonic distance sensor. We will briefly look at the basic principles of such a sensor before we move on to describe two different ways in which this can be implemented using an AVR microcontroller. At the end of the video, we will also show you where you can find the source code for this example. Let us start by explaining the measurement principle. An ultrasonic pulse is produced that propagates through the air. When it hits an object or a wall, it is partially reflected back towards the sensor. The distance can then be calculated as a product of the travel time of the pulse and the sound velocity. The velocity of sound is dependent on temperature, and it is therefore important that a temperature measurement is performed to ensure accurate calculations. To build an AVR-based ultrasonic distance sensor, we need the following hardware components: an ultrasonic transducer to send and receive the signal, circuitry components to amplify the signal and filter out noise, buttons and an OLED display for user interaction, and the AT-Tiny817 microcontroller to run the application and tie everything together. All of these components have already been implemented in Microchip's rangefinder field engagement board, which is described in the AT-Tiny817 product page. A link is available in the video description. Let us first consider a simplified implementation that uses polling and is running on the main core thread. The first thing we do is to start a timer, which will allow us to measure the travel time of the pulse. The ultrasonic transducer requires a 40 kHz driving voltage, which can be generated using a loop to toggle one of the device output pins. After the resulting pulse train is transmitted, we wait a short delay to ensure that the transducer has stopped oscillating before we start polling the analog comparator to check for a reflected signal. When the reflected signal is detected, we poll the timer to get the elapsed time and perform a temperature measurement using the built-in temperature sensor in the device ADC. This allows us to calculate the distance using the formula we looked at previously, and we can output the results to the OLED display. A check for user input is conducted, and the process is started all over again with a new pulse train for continuous measurements. This core-based implementation can be made to work, but it has some disadvantages that will affect the measurement accuracy. Since the whole application is heavily reliant on the core, it is not possible to use the core for any other processing simultaneously without affecting the performance and accuracy of the distance sensor. Additionally, several parts of the implementation give rise to non-deterministic behavior. The use of polling can cause user input to not be registered properly. The core is unable to do two things simultaneously, and the timer can therefore not be started in perfect unison with the ultrasonic signal. Similarly, the elapsed time and the temperature will be measured slightly after the signal is detected. The use of analog comparator polling to detect the return signal could cause us to miss some of the signal peaks depending on how the waveform lines up with our sampling points. Even at the highest supported polling rate, it is likely that we would miss several peaks, which would cause measurement errors of several centimeters. This implementation does work, but a much better solution can be achieved if we use the core-independent peripherals of the microcontroller. The core can then remain in sleep mode most of the time and only wake up to handle distance calculations and OLED outputs. Everything else is offloaded to the peripherals. We will now take a brief look at the components that make this possible. We start with the interrupt system. In normal operation, information is sent between the core and the various peripherals. The core interprets the information and provides instructions for the peripherals to execute. However, in many applications there are times when there are no calculations to be performed and the peripherals are simply waiting for some external input. In these cases, it would be beneficial to put the core in sleep mode, that is, disabling it temporarily, as this reduces power consumption. Different sleep modes are available on the AVR microcontrollers, and the interrupt system allows peripherals to wake up the core when certain conditions are met, allowing regular operation to continue. Interrupts can also be used while the core is awake and provides a direct way for the peripherals to notify the core about important events, which greatly improves the responsiveness of the device. Peripherals can perform a wide range of tasks independently of the core. In our application, we will for example be using the timer counter peripheral to generate a continuous 40 kHz waveform. The resulting waveform displays significantly less jitter than a waveform generated by toggling a port using the core and delays. The custom configurable logic, or CCL, allows us to define truth tables and simulate logic circuits. They can be used to turn a pin high or low depending on the state of 2 to 3 other signals. The waveform in our distance measurement device should not be continuously output to the transducer, since we also need it to receive the return signal. If we use a second timer counter peripheral to generate a masking signal, we can then input both to a CCL in order to get the output signal that we want. Similarly, we can configure the components that receive the return signal to only work during an allocated time frame. This is important since the transducer input and output are both sent over the same circuit. In order to use the CCL, we must also have a way to route signals between the different peripherals. This is done through the event system, which allows direct core-independent communication. Instead of the traditional buses, where communication primarily occurs through the core, we can send and receive information between the peripherals directly, even when the core is asleep. The event system of the ATtiny817 has a total of 6 event channels, and by configuring this system correctly, we can handle all timings and waveform generation without the core. Only 2 of the channels are needed for our distance measurement application, one between the CCL and the TCD, and one between the ADC and the TCD, leaving the 4 remaining channels open for other purposes. Let us now take a look at how we can use interrupts, the event system, and the core-independent peripherals to make a better and more deterministic implementation. This schematic shows how everything is connected in our example, and we will walk through how it works step by step. The TCB generates a continuous 40 kHz signal, which is input directly to the first CCL block. The TCD generates a masking signal, which is input to both CCL blocks. It controls when the 40 kHz signal should be let through and when the input signal should be analyzed. The TCD is also connected to the RS latch, which is used to start and stop the timer. We start with only the 40 kHz signal. When the output signal mask is enabled, the transducer starts transmitting the ultrasonic pulse strain. At the same time, the RS latch is reset, which causes the TCD peripheral to start counting. The masking signal disables the output, and we wait for the reflected signal to return. The input signal mask is enabled after a short delay to ensure that the transducer is no longer oscillating due to the output signal. When the signal returns, the conditions for the bottom CCL is met and it outputs a signal that sets the RS latch. This causes a second trigger of the capture port in the TCD peripheral, allowing us to measure the travel time of the pulse very accurately. The core is woken up by the TCD and reads the travel time. It also requests a temperature reading from the ADC peripheral and looks up the relevant sound velocity. The total distance is calculated and is promptly output to the OLED display. Direct communication between the core-independent peripherals enables this implementation to have more accurate and deterministic signal detection than the core-based implementation we discussed earlier in this video. Time-critical polling is mostly eliminated, and signal delays are shorter and more deterministic, which makes fine-tuning easier and improves performance. In this video, we have discussed how the measurement logic is implemented in Microchip's rangefinder field engagement board, which can be used as inspiration for your own projects. The source code for this example is available through Atmel START and can be found by searching for ATtiny817 ultrasonic. The application note can be found by opening the user guide and searching for the listed document. Two source code versions are provided. One barebone version, which initializes the device by writing directly to the registers, and one featuring peripheral initialization drivers, which is likely easier to understand and can be explored using the graphical Atmel START interface. We hope that you have enjoyed this video and that the core independent peripherals can be of use to you in your future projects. Please see the video description for further documentation, and don't forget to check out the source code in Atmel START or take a look at the associated app note.